Welcome to GCP Advanced Routing. Welcome everyone. Today we're diving deep into one of Google Cloud Platform's most powerful networking features, advanced routing using network tags and route priority. Think of this as going beyond basic send traffic to this destination and moving into send traffic from these specific virtual machines through this particular path based on our business requirements. By the end of this session, you'll understand how to implement source-based routing policies, create redundant network paths, and force specific traffic through security appliances, all using GCP's native routing capabilities. This is essential knowledge for any cloud architect designing secure, scalable network topologies in Google Cloud. The traditional routing challenge. Let me start with a scenario that probably sounds familiar. You have multiple virtual machines in your VPC, and you want different security policies for different types of workloads. Maybe your web servers can go directly to the internet, but your database servers must route through a firewall appliance for deep packet inspection. Or perhaps you want some traffic to use a VPN for compliance reasons while other traffic uses the standard internet gateway. With basic destination-based routing, all virtual machines follow the same path to reach the same destination. This diagram shows the limitation. Every virtual machine heading to the internet takes the same route, regardless of security requirements. This is where GCP's advanced routing features become game changers for enterprise network design. GCP's solution: tags and priority. Google Cloud solves this with two elegant mechanisms that work together beautifully. First, we have network tags. Think of these as labels you put on virtual machines to group them logically. A virtual machine tagged with secure workload can be treated differently from one tagged public-facing. Second, we have route priority, a numerical value that determines which route wins when multiple routes could handle the same traffic. Lower numbers win, so a route with priority 100 beats one with priority 1000. When you combine these two features, you get incredibly granular control. You can say traffic from virtual machines with tag X should use route Y, and that route should take precedence over the default path. This opens up possibilities for zero-trust architectures, compliance-driven routing, and sophisticated traffic engineering. Route priority deep dive. Let's understand exactly how route priority works, because this is fundamental to everything we'll build today. GCP uses a two-step process for route selection. Step 1 is always destination specificity. A route to 10.0.1.0/24 will always beat a route to 10.0.0.0/16 for traffic going to 10.0.1.5, regardless of priority. Priority only comes into play when multiple routes have the exact same destination prefix. So, if you have 3 routes all pointing to quad 0/0, the default route, then priority determines the winner. The key insight is that priority is an integer starting from 0, and lower numbers win. So priority 100 beats priority 1000. The default Internet Gateway route has priority 1000, which means any custom route with priority less than 1000 will override it. This is how we can intercept traffic and redirect it through our custom paths. Priority in action example. Here is a real-world example that shows priority in action. Imagine you are building a security architecture where most traffic goes directly to the internet, but you want a backup path through a VPN tunnel, and you want critical traffic to go through a firewall appliance. All 3 routes have the same destination, quad 0/0 for internet traffic. The route priorities determine which one actually gets used. The firewall route has priority 900, making it the highest priority. The default internet route has priority 1000. The VPN backup has priority 2000, making it the lowest priority. Without network tags, all traffic would use the firewall route because it has the lowest priority number. But we will see in the next few slides how tags let us be selective about which virtual machines use which route. This layered approach gives you both redundancy and security. If the firewall fails, traffic fails over to the internet gateway, and if that fails, it goes through the VPN. Understanding network tags. Now let's dive into network tags, which are the key to implementing source-based routing policies in GCP. A network tag is simply a string label that you assign to a virtual machine instance. You might tag virtual machines with labels like web tier, database tier, PCI compliance, or high security. These tags have no inherent meaning. They're just labels you define based on your architecture. The magic happens when you reference these tags in your routes. When you create a route with a specific tag, that route only applies to traffic originating from virtual machines that have that exact tag. This is fundamentally different from firewall rules, where tags often define the target. With routing, tags define the source, meaning which virtual machines the route applies to. You can assign multiple tags to a single virtual machine, and a single tag can be assigned to multiple virtual machines. This gives you tremendous flexibility in grouping and managing your routing policies. Tags for source-based routing. This diagram perfectly illustrates how network tags enable source-based routing. We have two virtual machines in the same subnet, but they behave completely differently when reaching the internet. The virtual machine tagged with proxy traffic follows a custom route that sends its traffic through a proxy appliance. This proxy might provide caching, content filtering, or compliance logging. The untagged virtual machine follows the standard default route directly to the internet gateway. Same destination, but completely different paths, based purely on the source virtual machine's tag. This is incredibly powerful for implementing security policies. You can ensure that sensitive workloads always route through security appliances, while less critical workloads take the direct path for better performance. The key insight is that both virtual machines exist in the same network and subnet, but their tags determine their routing behavior. This gives you micro-segmentation at the routing level. Real-world implementation strategy. Now let's look at a comprehensive real-world implementation that combines both tags and priority. This is the kind of architecture you'd build for an enterprise application with different security zones. Our goal is to force all internet-bound traffic from high-security virtual machines through a central firewall appliance, while allowing standard virtual machines to use the default internet gateway for better performance. The architecture uses three key components: tagged application virtual machines that need inspection, a firewall appliance virtual machine that acts as a security gateway, and custom routing rules that tie it all together. Notice that we're using both tags to select which virtual machines the rule applies to, and priority to ensure our custom route overrides the default internet route. This pattern scales beautifully. You can have multiple tag-based routes for different security levels, compliance requirements, or performance characteristics. Architecture components breakdown. Let's break down each component of our tagged routing architecture to understand how they work together. First, we have App Virtual Machine 1 tagged with Inspect Traffic. This tag marks it as a high-security workload that requires all internet traffic to be inspected. The tag is the key that links this virtual machine to our custom routing route. App Virtual Machine 2 has no special tag, so it follows standard routing behavior and goes directly to the internet through the default gateway. This represents your standard workloads that don't need special handling. The Firewall Appliance Virtual Machine is the security gateway. It has IP forwarding enabled, which is crucial. This allows it to receive traffic from other virtual machines and forward it onward to the internet after applying security policies. Finally, we have our custom route with tag, Inspect Traffic, and Priority 900. This route captures traffic from tagged virtual machines and directs it to the firewall appliance, overriding the default internet route. The beauty of this design is its simplicity and scalability. Adding more virtual machines to the inspection policy is as simple as adding the tag. Step-by-step implementation. Now we're ready to build this architecture from scratch using G-Cloud commands. I'll walk through each command, explaining exactly what it's doing and why each parameter matters. We start by creating the VPC network in custom mode, which gives us full control over subnetting. Then we create our subnet with a private IP range that will house all our virtual machines. Firewall rules are essential for basic connectivity. We need to allow internal communication between virtual machines and SSH access for management. These rules apply to the entire network regardless of tags. Then, we create 3 virtual machines. The firewall appliance with IP forwarding enabled, the tagged application virtual machine that will use the custom route, and the untagged virtual machine that will use default routing. Finally, we create the custom route that ties everything together, specifying the tag, priority, and next hop instance. Each of these commands has specific parameters that are crucial for the setup to work correctly. Let them in detail. Creating the firewall appliance virtual machine. Now we're creating the heart of our security architecture, the firewall appliance virtual machine. This virtual machine will act as a security gateway that inspects and forwards traffic from our tagged virtual machines. The absolutely critical parameter here is can IP forward. Without this flag, the virtual machine cannot route traffic for other virtual machines. It can only handle traffic destined for itself. With IP forwarding enabled, this virtual machine becomes a router that can receive packets from other virtual machines and forward them onward. We are using a standard Debian image, but in production, you would typically use a specialized security appliance image from vendors like Palo Alto Networks, Fortinet, or Checkpoint. The machine type E2 medium provides sufficient resources for basic firewalling and NAT functions. Notice we are placing it in the same subnet as our application virtual machines. This is important because our custom route will reference this virtual machine as the next hop, and it needs to be reachable from the source virtual machines. Creating application virtual machines with tags. Here, we create 2 application virtual machines that demonstrate the power of tagged routing. These virtual machines are identical in every way except for their network tags, yet they will behave completely differently when trying to reach the internet. Application virtual machine 1 gets the crucial tags parameter. This single tag will cause all its internet-bound traffic to be routed through our firewall appliance. The tag is the bridge between the virtual machine and our routing policy. Application virtual machine 2 has no tags, making it a standard virtual machine that will use the default internet route. This represents your typical workloads that do not require special security handling. Both virtual machines use the same machine type, image, and subnet. The only difference is that tag, but it completely changes their network behavior. This is the beauty of GCP's tag-based routing, massive flexibility with minimal configuration differences. In a real environment, you might have dozens of virtual machines with the inspect traffic tag, and they would all automatically inherit the same routing behavior. The core route configuration. This is where everything comes together. It is the custom route that implements our tag-based routing policy. Let me break down each parameter, because they are all crucial to making this work. The destination range quad 0/0 means this route applies to all internet-bound traffic. We are not being selective about destinations. We want to catch all traffic going to the internet. The next hop instance parameter tells GCP to send matching traffic to our firewall virtual machine instead of the internet gateway. This virtual machine becomes a routing hop in the path to the internet. The tags inspect traffic parameter is the selector. This route only applies to traffic originating from virtual machines that have this exact tag. Without this parameter, the route would apply to all virtual machines in the network. Finally, Priority 900 ensures this route takes precedence over the default internet route, which has priority 1000. Lower numbers win in GCP's priority system. Understanding route parameters. Let's dive deeper into each parameter of our route creation command, because understanding these details is crucial for building robust routing architectures. The network parameter specifies which VPC this route belongs to. Routes are VPC scoped, not global, so you need to specify the target network. Destination range uses CIDR notation to specify which traffic this route handles. Using quad 0/0 means all IPs. This is a catch-all route for internet traffic. The next hop instance parameter is powerful. It lets you route traffic through any virtual machine in your network that has IP forwarding enabled. You must specify both the instance name and its zone. Tags create the selectivity. Without tags, this route would apply to all virtual machines. With tags, it only applies to virtual machines that have the specified tag. This is what makes source-based routing possible. Priority is the tiebreaker when multiple routes have the same destination. Remember, lower numbers win, and the default internet route has priority 1000. Traffic flow analysis. Let's trace exactly what happens when our virtual machines try to reach the internet. This traffic flow analysis shows how tags and priority work together to create sophisticated routing behavior. When app virtual machine 1 tries to reach 8.8.8.8, GCP's routing engine looks for applicable routes. It finds two routes with destination quad 0/0, our custom tagged route and the default internet route. The tagged route only applies to virtual machines with the inspect traffic tag. Since app virtual machine 1 has this tag, the route is applicable. The priority 900 beats the default route's priority 1000, so the tagged route wins. Traffic flows to the firewall appliance virtual machine, which must then forward it to the internet. The firewall virtual machine itself uses the default route because it doesn't have the inspect traffic tag. App virtual machine 2 has no tags, so the tagged route doesn't apply to it. Only the default internet route is applicable, so traffic goes directly to the internet gateway. This creates a selective security policy where only tagged virtual machines go through inspection, while others maintain direct internet access for performance. Firewall virtual machine configuration. Having IP forwarding enabled on the firewall virtual machine is just the first step. The virtual machine also needs to be configured to actually process and forward the traffic it receives. This requires configuring the virtual machine's operating system to act as a router and NAT gateway. The first command enables IP forwarding in the Linux kernel. This tells the operating system to route packets between network interfaces instead of dropping them. The IP tables command sets up network address translation, NAT. When the firewall virtual machine receives traffic from 10.10.10.5 destined for 8.8.8.8, it needs to replace the source IP with its own IP address so that return traffic comes back to it. Without NAT, the internet would see traffic coming from 10.10.10.5, but that's a private IP that can't be routed back through the internet. The firewall virtual machine's external IP becomes the source IP for all forwarded traffic. In production environments, this is where you'd configure your security policies, deep packet inspection, content filtering, or other security functions before forwarding traffic onward. Route verification and testing. After implementing our routing configuration, it's crucial to verify that everything is working as expected. These commands help us inspect the routing table and test our configuration. The G-Cloud Compute Routes List command shows all custom routes in your project. You should see your tagged route listed with the correct priority, destination, and next hop configuration. From within the virtual machines, you can use standard networking tools to verify the routing behavior. The IP route command shows the virtual machine's routing table as it sees it. Testing connectivity is important. Try reaching external destinations from both the tagged and untagged virtual machines. You should see different behavior based on the tags. Network monitoring tools in the GCP console can show you traffic flows and help you verify that traffic is indeed flowing through your firewall appliance for tagged virtual machines. Remember that routing changes can take a few minutes to propagate fully, so be patient when testing your configuration. Advanced routing patterns. Once you understand the basics of tagged routing, you can implement much more sophisticated patterns. Let me show you some advanced architectures that leverage these same principles. Multi-tier security is a common pattern where different types of workloads get different levels of security inspection. Web servers might route through a basic firewall, while database servers route through a more intensive inspection appliance. Compliance-driven routing is another pattern where certain workloads must route through specific geographic regions or through certified security appliances to meet regulatory requirements. You can also implement redundant security architectures where primary security appliances have backup routes with different priorities. If the primary firewall fails, traffic automatically fails over to a backup path. Cost optimization patterns use different routes for different traffic types. Perhaps bulk data transfer uses a slower but cheaper path, while interactive traffic uses the fast direct route. The key insight is that tags give you unlimited flexibility in grouping virtual machines, and priority gives you precise control over path selection. Troubleshooting common issues. Let me walk you through the most common issues you'll encounter when implementing tagged routing, because troubleshooting routing problems can be tricky. The number one issue is forgetting to enable IP forwarding on your next hop virtual machine. Without this, the virtual machine will receive the traffic but drop it instead of forwarding it. Always verify this setting first. Tag mismatches are another common problem. The tag in your route must exactly match the tag on your virtual machine. Tags are case-sensitive and must be spelled identically. Priority conflicts can cause unexpected behavior. If you have multiple routes with the same destination and same tags, the priority determines which one wins. Make sure your priorities are set correctly. Firewall rules can block traffic even when routing is configured correctly. Make sure your VPC firewall rules allow traffic between the source virtual machines and the next hop appliance. NAT configuration on the appliance virtual machine is crucial for internet-bound traffic. Without proper NAT, return traffic won't find its way back to the original source virtual machine. Use the GCP console's network monitoring tools to trace traffic flows and identify where packets are being dropped or misrouted. Best practices and production considerations. Before we wrap up, let me share some crucial best practices for implementing tagged routing in production environments. Documentation is absolutely critical. With complex routing policies, you need clear documentation of which tags do what, which routes have which priorities, and what the intended traffic flows are. Future administrators will thank you. Start simple and add complexity gradually. Begin with basic tagged routing for one use case, validate it thoroughly, then expand to more complex scenarios. Use consistent naming conventions for tags. Consider prefixes like security dash, compliance dash, or performance dash to group related tags logically. Monitor your routing behavior continuously. Set up alerting for when traffic patterns change unexpectedly, which might indicate routing issues. Plan for appliance failures. Your security appliances should be redundant, and you should have backup routes with different priorities to handle failures gracefully. Consider the performance impact. Adding hops in your network path increases latency. Make sure the security benefits justify the performance cost for your specific use cases. Test route changes in non-production environments first. Routing changes can have wide-reaching impacts that aren't always obvious.